On a street corner in Knoxville, Tennessee, a license plate reader pole stood like a piece of evidence. Later, the surveillance would be described as a safety or validation effort for an autonomous capability. But here's the controlled dread. What if the test didn't just monitor autonomy? What if it trained the loop that autonomy needs, using identifiers that were never meant to be weapon-grade inputs? So the question you asked is the question that matters. Did the Knoxville test use license plate readers to validate an autonomous weapon and accidentally expose the failure mode? Let's reconstruct what these tests reportedly did, how LPR data becomes a decision input, and why the watch the watcher stealing isn't paranoia. It's systems engineering. First, the Knoxville test in plain terms. License plate readers don't capture a whole scene for you to review later. They capture a compact identity, a plate number, time, and location, plus a confidence score. In practice, those outputs get associated to a track. This vehicle likely moved from here to there. Why that matters for autonomy is simple. Autonomy doesn't only react to its surroundings. It can be validated against expected behaviors. If the system is told, directly or indirectly, what vehicles are where, when, and how they move, then the evaluation becomes a feedback loop. An LPR record isn't just information, it's an operational key. Now look at the evidence framing investigators often use, because it shows how the pipeline was meant to work. Maps with coordinate pins, camera cluster silhouettes, timelines with signal pulse overlays, little bursts indicating capture to decision timing. In that view, the device isn't passive. It becomes a sensor node in an orchestration. And that orchestration is where autonomy testing can become an exposure event. If an LPR feed is treated as ground truth for who is present and where they're going, then those identifiers can be used to trigger cues, routing changes, tracking handoffs, or validation events tied to specific agents. The chain we're asking you to picture has steps, not vague data streams. Step 1. LPR capture. A plate is read, timestamped, and geotagged at the roadside. Step 2. Tracking association. The system links successive reads into a track, estimating continuity even when the vehicle isn't always visible. Step 3. Automated queuing or routing. This is the key step. The queue might be associate this track with a scenario participant, start the evaluation timer, or hand off the track to the autonomous stack. Step 4. Autonomous system validation. Then the autonomous system is tested against that track's expected behavior, how it interprets, how it predicts, and how it responds. When the output is used to steer the system's attention, it stops being mere observation. The system doesn't only detect vehicles, it operationalizes movement patterns. Once you can identify individuals persistently and associate them with a path, you can constrain or prioritize autonomy actions around them. Even if the stated goal was safety, the hidden risk is that safety logic and targeting logic share the same skeleton. Identify, predict, and act. In one case, the action is avoid. In another, it could become intercept or sequence. If the same association mechanism supports both, then you don't need evil intent for weaponization risk, only an unexamined assumption about how inputs are used. Controlled dread comes from realizing the system that makes roads safer can also be tuned to make tracking persistent. This is where privacy threat stakes become concrete. LPRs normalize persistent identification. A plate is a durable token. A token plus location and time becomes a behavioral record. In a benign world, that record helps traffic management. But in the autonomy world, identifiers can be repurposed as constraints. Follow this agent, exclude that vehicle from scenarios, or label that track as relevant for action timing. So the frightening possibility isn't that someone secretly reads minds. It's that identifiers created for one purpose become reusable primitives. The surveillance infrastructure teaches the system what to treat as an entity. And once that's learned, the autonomy loop has a shortcut. Which brings us to the cyber angle, the integrity gap. Automation depends on correct inputs and correct configuration. If the system believes an LPR association is trustworthy, it may route decisions based on it. An integrity gap appears when the autonomy pipeline lacks isolation, when monitoring data isn't sandboxed from action logic, or when confidence scores, error rates, and association mistakes aren't handled as first-class uncertainties. Misconfiguration or untested assumptions can turn monitoring into harmful behavior. If false associations are treated as truth, autonomy could validate the wrong scenario participant. Worse, it could learn operational patterns from the wrong entity. That's how surveillance becomes weapon-grade timing. Not by magic, but by brittle trust. Now consider the corruption and hidden power system incentives, because testing doesn't happen in a vacuum. Procurement and contractor testing incentives can shape what is publicly described. The public story might be about traffic safety, infrastructure evaluation, or research feasibility. But internal metrics are operationally decisive. A team can minimize what they publish about outputs while maximizing what they log internally. Association rates, queue timing accuracy, track continuity, and how often LPR fed tracks improved autonomy performance. The public sees a reader poll. The operational system sees a scoring function. And once internal metrics show that an LPR association improves outcomes, the pipeline can quietly migrate toward LPR-dependent queuing, even if the initial contract language never said autonomous queuing. So, what did Knoxville actually demonstrate, and what did it imply? We're careful here. The crucial evidence is the existence of an LPR test that produced geotemporal plate identifiers and linked them to vehicle tracks during an autonomy-related validation effort. If those outputs were used to queue, label, or verify autonomous system behavior, then the implied failure mode is straightforward. Surveillance can feed autonomy loops quickly and silently because the infrastructure already exists at street level. There's no need for the autonomous system to figure out which agent matters. The identifiers show up as an existing decision input. The practical implication is that autonomy isn't just tested in a lab anymore. It's validated against real movement, using devices that capture identities and motion in ways that are easy to scale. And that's why your question matters. Did the Knoxville test use license plate readers to validate an autonomous weapon and accidentally expose the failure mode? The more precise answer is, if the Knoxville autonomy validation used LPR outputs as a queuing or tracking association input, then it demonstrated a pathway from persistent identification to autonomy-relevant decision timing. Whether the intent was weapon or safety, the exposed failure mode is capability alignment. An architecture that links LPR identity to autonomous actions can be repurposed. The exposure isn't the plate reader itself, it's the coupling. So here's the safeguard challenge. What should have been required if the goal was truly limited safety validation? Audit trails that show exactly how LPR outputs are used, down to whether they triggered any routing, labeling, or action timing. Isolation of LPR outputs from autonomy pipelines, so monitoring cannot directly influence control decisions. Strict purpose limitation, enforced technically, not just contractually. Independent oversight with the authority to verify error handling, confidence thresholds, association rejection criteria, and uncertainty propagation. And public transparency about outputs produced, plate identifiers, timestamps, locations, and whether those records were retained or used to generate scenario labels. Ask yourself, were these safeguards present? And could an LPR-backed queuing path be ruled out? If we can't answer that, then the controlled dread is justified, because the surveillance infrastructure may already be compatible with autonomy loops we've never properly audited. If you want, reply with what you think the standard should be. Should any LPR-based identifier ever be allowed to influence autonomy decisions, even in tests? And if you've seen documentation about Knoxville's device outputs or queuing demonstrations, share it. The point isn't fear, it's accountability for the coupling that turns observation into action.